start this? I think, okay, yeah, I think I started. So the stage is yours, Hiroshima.
Yeah. So where is slideshow? Okay. Here. Okay. Okay. Here. No. Okay, let's start. Can you see this?
Yeah, I can see the slides.
Okay, slide. Okay. Okay, thank you very much for the very kind introduction, and thank you so much for giving me this very nice opportunity to give this talk in your laboratory, Neri-san. And yes, hello everyone. Yeah, so today I want to talk about this topic, which I am recently studying on. Uh, I start with the main topic of today's talk. The topic is a universal trade-off relation between symmetry, irreversibility, and quantum coherence. These three concepts are foundations in physics. Symmetry is the guiding principle in modern physics. It rules high-energy physics, condensed matter, and quantum information theory. Irreversibility is also central concept in thermodynamics and stochastic mechanics. It is also strongly related to quantum error corrections. By the way, if you have any questions, please interrupt me. Quantum coherence, I mean quantum superposition, is a unique property of quantum mechanics. It is the origin of quantum advantage in many tasks and the origin of many surprising phenomena in quantum mechanics. And the main topic of today's talk is a universal trade-off relation between these three concepts. And I also talk about its applications. This is the main result. The main inequality is simple, but it works as a unified theorem for symmetry-induced limitations on quantum information processing. For example, Wei theorem for measurements, Wei theorem for unitary gates, and Easton-Nero theorem for quantum error correcting codes. Furthermore, it also limits general quantum dynamics with symmetry, for example, quantum thermodynamics and black hole physics. I will explain about the details of the setup and results and applications to them and quantum thermodynamics. Before going to the details, I'd like to introduce my collaborators and papers related to this talk. This talk is based on these four papers. The first two papers are collaborated with Naoto Shiraishi and Keiji Saito. This paper is collaborated with Ryuji Takagi and Yui Kuramochi. And the fourth paper is also collaborated with Ryuji. And these three papers are accepted as regular talk in QIP. And these four papers treat a common topic, the resource cost of quantum channel implementation under global symmetry. From now, this talk follows this outline. First, I will explain about the background and motivation. And after that, I will explain setup and details and applications, and I will summarize my talk. Let's see the background and the motivation. The background is the relation between information processing and symmetry. The effect of symmetry on quantum information processing has been studied for a long time. It began by Wigner-Araki-Yanase theorem, which was given from 1952 to 1960. This theorem says that conservation laws provides a universal constraint on measurement accuracy. This theorem is itself interesting, and it is also an archetype of various relations between symmetry and quantum information processing. Indeed, the main result in this talk is can be seen as a generalization of the Wei theorem. So I firstly review the development of the Wei theorem and related previous results. Historically, the first study in this field was given by Eugene Wigner. In 1952, he considered an indirect measurement on a qubit system S, and he showed that under the conservation law of Z-spin, to implement the x-direction spin measurement without error on the qubit system, we need infinite size of the external device. So it is impossible. So he showed that under the conservation law of Z-spin, we can't measure x-spin without error. This result is very interesting, but it is limited to a qubit system and Z-spin conservation law and x-direction spin measurement. So it is very limited result. However, 80 years later, Araki and Yanase generalized Wigner's result. J showed that under the conservation law of A, we can't measure B without error if A does not commute with B. And today, this generalized result is called as Wigner-Araki Yanase. These two results are qualitative result, but Ozawa extended to that. In 2002, he generalized the Wei theorem to quantitative version. Namely, he showed that under the conservation law of A, in order to measure B, this is some physical quantity within finite error delta, we need variance of the conserved quantity inversely proportional to the error delta. Second, he extended the Wei theorem to the computation. He considered the implementation for C-not gate on 2-qubit system and shows that under the conservation law of Z-spin, in order to realize C-not gate within error delta, we need variance of Z-spin inversely proportional to delta.
Sorry, can I ask some quick questions on this?
Yeah.
So here when you measure the environment system, is it like the measurement of A operator or?
Yeah. So sorry. So you asked about here.
Yeah.
Sorry. So this is projective measurement on probe system. This is target system, and this is probe. This is measurement on probe system. And Ozawa assumes that the measurement on the probe system commutes with the conserved quantity on the probe system. So AE. Okay, and he calls that this assumption as Yanase condition. Wigner-Araki Yanase's Yanase condition. The reason why he called it is that Yanase assumed a similar condition in previous results, but indeed this Yanase condition is introduced by Ozawa. It is a little bit confusing.
I see. And when you say the variance of AE, does that mean the initial state of the probe should be?
Yes.
Okay, I see.
So you must prepare large variance on the probe system if you want to make the error small. Yeah. Thank you very much for the question. And Ozawa's discovery is very interesting because it implies a common restriction between measurement and computation. So for measurement, there is a trade-off relation between error and variance. And for C-not gate, there is also a very similar trade-off relation between error and variance. So there there are two natural questions. First, would a similar relationship hold for general unitary gate? If yes, then the similarity becomes complete. Because in this moment, this result is only for C-not gate. And the second question is this: is variance really good? Because variance can increase with classical mixture. So these trade-offs imply thermal noise can improve the accuracy of the measurement and computation, but it is a little bit strange. So fortunately, we can answer these two questions. First, there is a universal trade-off relation between error and variance for general unitary gate. And second, we can substitute quantum Fisher information, which is the good resource measure for asymmetry and quantum fluctuation of conserved charge for a variance part in the trade-off. So the required resource is indeed quantum fluctuation, only quantum fluctuation. It is natural because this trade-off relation implies thermal noise cannot improve accuracy. And there is similar trade-off relation between error and quantum fluctuation for error. So there is a common error coherence trade-off actually exists. So the second natural question is this: isn't there a more general restriction beyond measurement and unitary? Because measurement and unitary is very different operations. So maybe there is more general dynamics. And when we see other operations, indeed, there is a very similar type theorem. That is Eastin-Neel theorem. The target of the Eastin-Neel theorem is the error collection. And more particular, covariant code. In covariant code, in covariant code, we think some class of unitary gate. And when the unitary gates gives same result before the code and after the code, then we call the code channel as covariant code. And Eastin-Neel theorem says that the above covariant, the covariant code cannot, covariant code for continuous unitary representation cannot recover the qubit erasure error perfectly. This is a very famous theorem for error correcting code. So maybe some of you know that. But anyway, there is another very important extension, recent extension. The number of code qubit is inversely proportional to the recovery error. This is given by Feist and many researchers, but this is very important result. So now we have seen three very similar restrictions on different operations: measurement, unitary, and error corrections. And all of them says error is inversely proportional to some resource. So the last question is this: aren't these three special aspects of a single unified theorem? And the key idea to solve this question is that the errors in these three trade-off relations are kinds of irreversibility. Because measurement error is a kind of information loss, so it is a kind of irreversibility. And unitary error is also irreversibility because unitary gate is reversible dynamics. And recovery error for error correcting code is, of course, a kind of irreversibility. So, so we now give a conjecture. Under global symmetry, there is a universal trade-off relation between symmetry, irreversibility, and quantum coherence. In this talk, I report this conjecture is actually true. Now I have explained the background. Next, we see the details of the setup and results. Let us introduce our setup. We introduce two systems, A and B. These two systems interact with each other as unitary dynamics with a conservation law of X, which corresponds to some continuous symmetry. We can consider more general continuous symmetry, for example, in any types of Lie group symmetry. But for simplicity, we focus on this type U1 symmetry, U1 or R symmetry. And we fix, after the unitary, we divide the composite system AB into two systems, A prime and B prime. And we fix the initial state of B arbitrarily. Then the local dynamics from A to A prime is described as a CPTP map, E. For this situation, our main result always holds this inequality. Here, the quantity C is the change of a local conserved charge, XA, this one, by E. So from here to here. And F is the quantum coherence of the conserved charge, XP in here, B. This is asymmetry. This is measured by quantum Fisher information. And delta is the irreversibility of the local dynamics. And large delta is a positive constant. Let's see the definitions and important properties of these quantities one by one. We firstly explain the irreversibility delta. It is a function of the local dynamics E and test ensemble PK rho K. We can take this test ensemble freely, even if each rho K are not diagonal, are orthogonal each other. The formal definition of delta is this. Here, delta K is the recovery error for rho K. So we prepare some test ensemble freely, and we perform some CPTP map E. This is this. And then the initial states become different. And so we try to recover the initial state as close as possible by using the recovery map R. R can depend on the test ensemble, but it cannot depend on each rho K. Then we can define the recovery error for each rho K, each initial state. Here df is the purified distance, and this is Ullmann's fidelity. And we take the minimum average of delta K. Here R runs all CPTP map from A prime to A. The merit of this irreversibility measure is that it gives lower bounds for various irreversibility measures. For example, it gives a lower bound for entropy production, which is the standard measure of thermodynamic irreversibility. It also bounds the entanglement fidelity recovery error, which is used for a standard measure of error in quantum error correcting codes, and it also bounds the error of PETSMAP recovery, etc., etc. So we can substitute these quantities for here and use this inequality. And we also use quantum and F is the quantum coherence of the conserved quantity in B. We measure it by using quantum Fisher information. More precisely, we use SLD quantum Fisher information of the state family, of this state family. And the SLD quantum Fisher information is a standard measure of the resource in the resource theory of asymmetry. Indeed, this characterizes the optimal IID conversion rate in the resource theory of asymmetry for U1 case. U1 symmetry case. Sorry.
Can you go back to your previous slide? Just one.
Okay. This previous, you mean this?
This one, yes. Just a stupid question, because you mentioned that the property of this irreversibility measure is that it lower bounds all the quantities that people are interested in terms of like entropy production, etc. I'm just wondering if similar kind of upper bounds can be also made, like with, or is
Good
it not
question.
so
Good
much?
question. Very good question. And for this and this, maybe the answer is yes. Because when we choose the test state properly, then we can give upper bound. But maybe it is difficult to give upper bound of this by using this quantity. Because how to say, this bound is essentially a bound between fidelity or purified distance and relative entropy.
I see.
This bound is not so good, so maybe this is not a good bound.
Yes.
But important point is, with using this, at least we can see general relation between asymmetry and entropy production.
Yes.
Yeah. And let's see the next slide. Yeah, I explained that SLD Fisher information is a standard measure of resource in asymmetry. And it is also a standard measure of quantum fluctuation of conserved charge. I mean, F low x is equal to 4 times of minimum average of variance of the of x. Here, psi j is pure state. And Qj psi j is minimum decomposition. The Pj and psi j runs all possible decomposition of the state rho. Here, each psi j can be non-orthogonal ensemble. So we can consider f rho x as the part of the quantum fluctuation. So purely caused by quantum superposition. Yeah. Indeed, when rho is pure state, it is equal to 4 times of variance. And the third quantity is Xi. It is the degree of change of local charge. The formal definition is this. This is a little bit complicated, but we can simplify it. First, YA is the operator of the change of local charge. This is when we choose XA as Hamiltonian, then YA becomes work operator in quantum thermodynamics. And Next, when we choose the test states rho k are orthogonal pure states, C becomes this quantity. So this is a kind of the sum of absolute value of non-diagonal pairs in this basis. And another important property is when E changes XA non-trivially. I mean, when YA is not uh, proportional to identity. This means that the change of the conserved charge by the local operation is not just shift of origin. Then C is strictly larger than 0. So we can consider this as a degree of change of local charge. Now let's see our main result again. This square root delta is valid for arbitrary test ensemble. And this delta is valid for test ensemble which are orthogonal each other. I mean, if fidelity between rho k and rho k prime is equal to 0 when k is not equal to k prime. And the message of the main result is this. There are two messages. First, when C is strictly larger than 0, then delta is also strictly larger than 0. So when E changes the local charge non-trivially, E must be irreversible. This is the first message. If this part is strictly larger than 0, then delta is strictly larger than 0. Yeah, and the second message is the coherence in B, I mean F, can mitigate the irreversibility because when F becomes large, then the left-hand side becomes small, so we can make delta small. So the take-home message is this. Under global symmetry, local charge cannot be changed without irreversibility, but the irreversibility can be mitigated quantum coherence. So I call sometimes this trade-off relation as SIQ trade-off relation, symmetry, irreversibility, and quantumness. Now, I explained about the main results in this talk. So from here, I will explain about the applications of the trade-off relation. There are various applications. First, three applications are Eastin-Nil and Way, Eastin-Nil and Way and the unitary way, which is one of the main motivation of the trade-off relation. And we also, this trade-off relation can give also other applications in quantum thermodynamics, Hayden-Preskill model, and OT-OCA, etc., etc. But because of the time constraint, I only explain these three. There are two topics in this talk. Sorry, it's not two topics. Three applications from here. The application to quantum information processing is this. As I explained in introduction, there are three types of fundamental limitations on quantum information processing with global symmetry. Way theorem and unitary way theorem and Eastin-Nil theorem. Way theorem says that measurement error must be inversely proportional to coherence cost. And the unitary way is similar relation for unitary gates. And Eastin-Nil theorem is similar relation for covariant code. Error is inversely proportional to the qubits required by the code. And our trade-off relations behaves a unified term of these relations. It recovers and extends these results as corollary. This is the first application. The second application is application to finite time measurement and computation. The topic is the trade-off relation between speed and accuracy. There is a common sense about the trade-off relation between speed and accuracy. For example, if you increase shutter speed of camera, the resolution will decrease. But the question is there any actual trade-off relation between them? Important point is energy time uncertainty is not a trade-off relation of this type because energy time relation is just a trade-off relation for state. For state, it's energy fluctuation and measurement measurement accuracy on on how to say the accuracy of time measurement about time. But now I want to consider about the measurement trade-off relation between measurement speed and accuracy. So the target of measurement is not necessarily time itself. So any physical quantity is possible. And from the SIQ trade-off relation, we derive a general trade-off relation between accuracy and time of measurement, or time of quantum computation. This is the trade-off relation. E is the error of measurement or computation, and tau is the time of the measurement or computation. So accuracy. This trade-off gives a message that when we try to make error 0, then we need infinite length of time for measurement or computation. The proof sketch is this. We obtain this trade-off by using SIQ trade-off and a Lieb-Robinson bound. First, with using Lieb-Robinson bound, we evaluate the size of affected part in device from system, and we can estimate the amount of quantum Fisher information in this restricted part, and substituting the quantum Fisher information in this restricted part in here, then we obtain the accuracy, time and irreversibility trade-off relation. And in this paper, in another paper, the error and gate fidelity error are special case of irreversibility. So we can obtain the speed accuracy trade-off relation. Yeah, this is the proof sketch. And this is the second application. Yeah.
I have one.
Okay.
Sorry.
Yeah.
I have one question. So this trade-off does it depend on how the device looks like and how it interacts with the system, or the constants ABC
yes.
universal?
Yeah, indeed. So because we use the Lieb-Robinson bound, so so the details of the constant depends on the interaction mechanism or something.
But this form itself is just universal for
Yeah,
device.
very universal because as long as Lieb-Robinson bound holds. So the assumption is only this: there is conservation law. There are only two assumptions. There is a conservation law between system and device, and a device satisfies the Lieb-Robinson bound. Then this trade-off relation is given.
I see. Okay, thank you.
Yeah. important point is this is also a corollary of this. Yeah. And another good information about this is arbitrary measure and arbitrary disturbance of measurement is a special case of the irreversibility. It is shown in this paper. And now let's see the application to quantum thermodynamics. I think maybe some of you are interested in this part, so I will give the details of this application. Yeah. We first see the background. In resource theory, free states are easily prepared states, and free operations are easily performed operations. And each resource theory is structured based on the choice of these two. And in thermodynamics, free states are Gibbs states. And free operations are Gibbs preserving operations or summer operations. So there are two candidates of class of free operations. And the structure of the theory of quantum thermodynamics depends on which one is adopted. So clarifying the difference between these two classes is important. This is all information. This paper is published already. And main message is some Gibbs preserving operations require infinite amount of coherence cost, and thus they are physically infeasible. And let us introduce the definitions of summer operations and Gibbs preserving operations. When a CPTP map is realizable with an extra Gibbs state and energy preserving unitary, the CPTP map is a summer operation. And when a CPTP map preserves Gibbs state to Gibbs state, then it is a Gibbs preserving operation. The merit and demerit of these two classes are contrasting. And the merit of the summer operation is that its cost is clearly zero because Gibbs state is free state in quantum thermodynamics. And the demerit is it is difficult to analyze because it is a little bit complicated. And the merit of Gibbs preserving operation is that it is easy to analyze. And because of this merit, recent important works in quantum thermodynamics employ Gibbs preserving operations. However, the implementation cost of the Gibbs preserving operation is unclear. So, clarifying the coherence cost of Gibbs preserving operations is crucial. About the cost, the first question is, in the first place, are there really non-zero cost Gibbs preserving operations? It is maybe non-trivial question, and unfortunately, the answer is yes. Some Gibbs preserving operations require strictly non-zero strictly positive energetic coherence. This result is shown by Feist, Oppenheim, and Renner. They showed that there is a Gibbs preserving operation lambda such that to realize lambda with using an energy preserving unitary, the external state rho must satisfy rho does not commute with HB. So some Gibbs preserving operations require non-zero energetic coherence because this asymmetric state must have some non-diagonal part of non-diagonal elements in energy eigenbasis. So the next question is, how much coherence do we need? More precisely, the question is, to realize an arbitrary Gibbs preserving operation lambda, how much coherence is required? This is the question. This question is important because of two reasons. First, it is related to resource theoretic difficulty of implementing Gibbs preserving operations. Indeed, this question is an open problem in quantum thermodynamics. And it is also related to the possibility of infeasible Gibbs-preserving operations. If there are Gibbs-preserving operations requiring infinite coherence cost, they are infeasible. And this is also important because Gibbs-preserving operations are considered as free operations, which are believed as operations that we can easily perform. Then the question is, now I summarize the questions and show show our answer. The question is, are there infeasible Gibbs-preserving operations? The answer is yes. Some Gibbs-preserving operations require infinite energetic coherence, and thus they are physically infeasible. Important point is there exists an infinite number of such cost-diverging Gibbs-preserving operations. And there are tuples, rho and sigma, such that the transformation from rho to sigma is possible by cost-diverging Gibbs-preserving operation, but impossible by finite cost Gibbs-preserving operation. So limiting free operations to Gibbs-preserving operation with a finite resource changes the theoretical structure of quantum thermodynamics in the sense of the possibility of the state transition. To derive this result, we use the trade-off relation again. As I explained, this trade-off relation unifies these wave-type theorems. And this Gibbs-preserving operations result is also derived from this result. So we can say this wave-type theorem, this result as a wave-type theorem for Gibbs-preserving operations. Now let's see the details of the application. Let's see the setup. We consider Gibbs-preserving operation from A to A prime, and its implementation with using energy-preserving unitary. Then we need some external state, rho B. The goal is to evaluate the coherence cost of lambda. The coherence cost means the minimal sufficient amount of coherence in here to realize the desired Gibbs-preserving operation. In the next slide, we define the coherence cost of channel. As we employ quantum Fisher information as the energetic the measure of the energetic coherence. Let's define the coherence cost of quantum channel. Here we define not only the non-zero error implementation, but also cost of approximate implementation. We say this tuple realizes the target desired operation lambda within error epsilon when this U and rho B realizes lambda within the error epsilon in the sense of the gate fidelity error. And when U satisfies the energy conservation. And we define the cost of approximate channel implementation as minimum quantum Fisher information in rho B for all tuples which realize the desired operation lambda within error epsilon. By definition, the non-zero error cost is a special case of this definition. Now we introduce our main result. Our result is divided into, not main result, but a main result in applications. So our results are divided into three theorems. The first theorem is this. If systems A and A prime satisfies this inequality, then there exists cost diverging Gibbs preserving operation from A to A prime. This condition is easily satisfied. For example, when HA is equal to H prime, then this condition can be related to this condition with energy eigenvalues. And for example, in this case, non-degenerate three-level Hamiltonians, this inequality always holds. This condition always holds because this part is this, and this part is this, and this part is this. So this inequality holds. And so this condition holds for arbitrary non-degenerate three-level Hamiltonian. And whenever HA and HA prime has at least three different eigenvalues, there are cost diverging Gibbs preserving operation from A to A prime. Furthermore, we can show that even for two-level system, when the energy gap of the initial Hamiltonian is larger than the final Hamiltonian, the original condition holds, and thus there is a cost diverging Gibbs preserving operation. So let's see that we assume that the energy gap of initial Hamiltonian is larger than that of final Hamiltonian. Then the eigenvalue of Gibbs state is this one is smaller than this one, this part, and this one corresponding to this part is larger than this one. And so there exists a cost diverging Gibbs preserving operation even on a qubit system. So we can say that there are cost diverging Gibbs preserving operation almost arbitrary systems. And the similar relation for state transformation is also can be shown. When the systems A and A prime satisfy the same condition as the theorem 1, then there exists set or rho and on A and sigma on A prime that such that a rho to sigma can be realized only by cost diverging Gibbs preserving operation. Again, because this condition is easily satisfied, there are infeasible state transition between almost arbitrary A and A prime. And in the end, we can derive the approximate, upper and lower bound of the cost of the approximate implementation of such cost diverging Gibbs preserving operation. Yeah, from the main result, we can derive the lower bound, and we can also derive upper bound from another result. Then important point is the leading order is almost same, except for the constant 2. So, from this result, we obtain that the cost is inversely proportional to the square of the error, and the n is the system size. We can also show that this scaling is the worst in all approximate implementation of all CPTP maps. So Gibbs preserving operation includes the most costly class in all CPTP maps. Let's see the proof sketch, or very rough proof sketch of the main theorem. As I explained, this theorem 1 for Gibbs preserving operation is a corollary of this trade-off relation. So we can here we show the strategy of the derivation. Yeah, so this direction. The point is from the SIQ trade-off relation, we can give lower bound of coherence cost of arbitrary channel with using its irreversibility and constant and quantity C. Yeah, this is irreversibility. So sorry. This is here we use other PowerPoint slide. So I just repeat this explanation. But okay. The important point is this it is inversely proportional relation. So when there is a CPTP map, essentially Gibbs preserving operation satisfying C is strictly larger than 0 and delta is equal to 0, then its cost diverges. That is the message of the main result in the trade-off relation in this. So we only have to make a general method to construct such Gibbs preserving operations. The strategy is this. When a channel lambda maps orthogonal pure state psi and phi to orthogonal states, then delta becomes 0 for such test ensembles. Sorry, such test states. So measurement and prepare channel is good candidate. When a measurement prepare channel lambda satisfying this and this, sorry, this is not psi, this is phi, this one. Then the gamma satisfies this zero irreversibility. And in this measurement and prepare channel, if we can show this holds, then this C is strictly larger than 0 for this gamma. And many measurement and prepare channels can be written as Gibbs preserving operation. So maybe we can find good measurement and prepare channel as Gibbs preserving operations. Indeed, we can construct such a measurement and prepare channel. Let's see one example. Let us consider four-level system, and the four-level system has two degenerated states as ground states. For this system, the channel that we seek is this measurement and prepare channel. Here, this P plus and P minus are projections on these two states. And this term is an additional term, which makes the channel gamma Gibbs preserving. By derivation, this channel gamma maps psi plus to 0a, this from this part. And it also maps psi minus to 0b. Therefore, this and this holds, and thus lambda is strictly 0. Sorry, lambda, not lambda, sorry. Delta is strictly 0. And C is strictly larger than 0. And furthermore, by definition, lambda, sorry, not lambda, gamma maps gives state to Gibbs state because of this term, this additional term. Therefore, this gamma is Gibbs preserving operation, and thus gamma is an example of cost-diverging Gibbs-preserving operations. Yeah. Now I summarize my talk. We find a universal trade-off relation between symmetry, irreversibility, and quantum coherence. It has various applications, so measurement and error correcting cause, and etc. And the series of direct application of this trade-off relation is this. Today I explain about this and this and this, but there are some applications. And there might be more applications, so I hope to deepen discussion with all of you here. Thank you very much.
Thanks, Hiroyasu. That was a very nice talk. I guess now we open some time for questions. Feel free to just ask.
Yeah, maybe I'll start. So in this thermal, cost of Gibbs preserving operations, but it's a coherence cost thing, right? There's kind of like this step where you have a dependence in the epsilon, like you allow some epsilon error, and then like you can quantify how much coherence you need if you just want to implement it by up to some epsilon. Like where to get that? Like how do you show this epsilon dependence?
Okay. That is a good question. So in this strategy, I only explain about the cost diverging property for zero error case. So you asked about the finite error case. Indeed, the point is the irreversibility of gamma is strictly zero. Then the error of gate fidelity error of the target gamma. So a gate fidelity error of implementation of gamma, I mean epsilon, is lower bounded by the irreversibility of realized operation. Okay, maybe I have
Yeah, sorry.
I have to put.
Because I guess the key question is that this inequality that you have.
I will write here. Okay.
Yeah. Okay. Sorry.
Yeah. No. So now delta gamma and lambda is equal to 0. Okay. And now we try to implement this, but the operation implemented operation is this.
Yeah.
And the gate fidelity between the ideal operation gamma and the real operation gamma prime is epsilon. This is the situation. Then the point is epsilon is lower bounded by gamma prime of the delta. So again, we can use the SIT trade-off.
Okay.
And yeah.
It was over. Yeah.
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 That is the reason.
And like all these terms on the right hand side, it's gonna be kind of also continuous-ish. Like you can bound.
So sorry, please say again.
All these terms on the right hand side, the C, F, and delta, you can relate it to the C, F, delta.
Very good question. Very good question. Yes, yes, indeed. So this is just a constant. Yeah, this is independent from gamma or gamma prime.
Yeah.
Independent.
And I suppose F is also independent.
This is just cost. So
yeah.
This is gamma prime. And so the question is whether this is continuous for here. And the answer is yes.
Okay. Okay. All right, cool. Thanks.
Thank you.
Can you maybe explain a bit more about like when C becomes zero or like when it's non-zero? I assume that when you have a covariant channel, this C is always zero, but it's not like if and only
No,
if, right?
no. Indeed, no. So when even when the channel is covariant, she is not not zero.
Oh,
Yeah. So that is important point. That is why this trade-off relation can recover the Easton-Neel theorem. Okay.
see.
Can I erase it?
Yeah,
Yep,
yeah.
yep.
Okay.
So you're saying that basically the fact that you have infinite cost channels
Mhm,
for Gibbs preserving operations,
mhm.
it's not only just Gibbs preserving operations, but also Gibbs preserving and covariant operations. So
Sorry. Please say again. So you ask cost. Uh,
so there
sorry.
are your result is that there are cost diverging Gibbs preserving operations.
Yes. Non-covariant Gibbs preserving operations. And if covariant Gibbs preserving operation you consider, then cost does not
That's not diverge.
diverge. Yeah. Of course, and the cost can be zero.
Right.
So now I'm afraid that I misunderstood the previous Son-san's question.
Oh, my question was like what was the
You asked
exact
she?
condition when C becomes zero? Yeah.
Yeah.
The
Okay. So then I did not misunderstand.
mm.
Yeah, she can be strictly larger than zero, even if lambda is not covariant. Sorry, not even if lambda is covariant.
Huh.
In this case, f can be zero because this is the cost of the channel. And when we consider a covariant channel, we can always make the cost zero with taking a good implementation. So when we consider the covariant operation, this part becomes zero.
Mm.
So the inequality becomes like this. This is constant. So the message
Okay.
is when lambda is covariant and when she is strictly larger than zero, we can take such examples. Then irreversibility cannot be zero.
So C was some coherence, right?
Coherence. Yeah.
Mm.
She is how to say. The work operator of okay. She is non-diagonal part of the work operator. Work operator is the difference
Mm.
between the initial conserved quantity and final initial conserved quantity and final conserved quantity.
Mm.
Oh, my iPad pencil's power empty becomes empty. So sorry, please wait a little bit. Maybe it is okay. Yeah. So okay. So she is. Please see the definition.
so many pages.
Yeah, sorry.
No, no.
Okay, this one.
Ah,
So maybe you can consider this one. YA is the operator of change of local charge.
mm-hmm.
And this psi k is some test ensemble. Yeah, if you consider pure test ensembles, then she becomes this. So,
So okay.
yeah. So this is a non-diagonal part.
Mm.
This is non-diagonal part, like here and here.
And this local charge is not necessarily zero when you
Yeah,
have
yeah, yeah, yeah,
covariant channel.
yeah, yeah, yeah,
Okay.
yeah, 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 yeah.
Mm.
So, indeed, this inequality. Can you see this? Okay.
Uh,
So this inequality is uh, uh, some extension of Easton-Neal theorem. You can consider it. From this inequality, you can derive Easton-Neal theorem and for both quantitative version and no, qualitative version. Because covariant code is covariant operation.
mhm. And Easton-Neal theorem
Yeah,
follows
Easton-Neal theorem
because
is the number of qubit is inversely proportional to the recovery error. Recovery error is lower bounded by delta. So this is, and large delta is a qubit number.
okay.
Yeah.
I see. Right. Now I see. Thank you.
Mhm.
Hi, I got a question.
Yeah.
For cost diverging, do you mean it's impossible to implement it physically?
Yeah.
Then why do we want to construct the cost diverging operation? Why don't we just focus on finite cost operation?
Sorry.
Why do we want to construct the cost diverging operation?
Good question. If you don't want, for example, do quantum computation, then a cost diverging of operation is not necessary. But for example, let us consider superconducting qubit. In superconducting qubit, there is some two level, and there is a difference between energy level. So energy gap exists. And let us consider the so bit flip unitary. In this case, she is strictly larger than zero. So this unitary, bit flip unitary, is cost diverging. So cost diverging, so maybe cost diverging operations are important for information processing or quantum computation. So we want to realize it. Is that is it does it work for you to work as the answer to your question?
So the cost is not like the number of qubit is some different.
Cost is quantum fluctuation in the uh, beam to the superconducting qubit. when we try to realize bit flip unitary, we use some so coherent light to qubit system, superconducting qubit. So then F describes as the amount of the coherence, fluctuation of energy in the coherent light. So this gives some relation between the number of the light particle and error. Not light particle. Well, my English is very broken. So photons, sorry, photons and error. Yeah, for example. So
But this divergence is only when you have the symmetry, right?
Yes. But indeed, so is superconducting qubit and coherent light satisfy energy conservation law. So there is symmetry.
Okay.
Fortunately, the error can be made very small when we make the light enough strong. Yeah, but there is error and there is fundamental limit.
Okay, I see. Thank you.
So Hiroyasu, sorry, Ray, you are unmuting.
Yeah.
Yes, sorry. I guess before you close, the closing question, maybe, or not, I don't know. Given the group's obsession with catalysis and such related things, do you think you can kind of like strengthen this result to cover like, okay, maybe you need infinite coherence cost. Like in the beginning, you need a state with infinite coherence, but maybe there's a way to quantify how much coherence is actually consumed in this protocol, and then maybe it's doable actually catalytically. For example,
Yeah. Good question.
Right? Is there a pathway to like strengthening this result to cover those type of scenarios also, or it's more difficult?
Very good question. And indeed, previously Nelly-san asked me similar question, and the answer is this. Almost of these costs can be used as catalytic way.
Okay.
Catalytic way. So maybe we can recycle it, reuse it. Yeah.
Okay.
Yeah.
So, okay. So if you only look at the kind of resources consumed, it's actually like any Gibbs preserving operation can be implemented at zero catalytic cost.
No. So catalytic cost mean so the amount of consumed catalyst, you mean?
Yeah, let's say I define catalytic cost, or like some people would say amortized, right? Look at the Fisher information in the final state of this catalyst,
Before
which
and
may
after.
not be catalyst, before and after. Yeah.
Okay. It depends on situation, maybe. But maybe we can make some. Sorry. Maybe in many cases, we can make the catalytic cost small.
Okay.
Yeah.
Because I guess like you can kind of construct a pathological example or something, right? You just have two systems that are both infinite coherence, and then you just use one part of them. Then the cost is like infinite minus infinite, which can be anything you want, I guess.
But
I don't know, something more physical. Is there?
Two systems.
Two systems, infinite coherence, both of them.
Yeah, okay.
And then you use the coherence in B to implement a Gibbs preserving operation. And then if you look at the I'm not sure catalytic cost is the right word here, but like amortized cost, right? Then it's gonna be like final coherence infinite minus initial coherence, which is also infinite. So it's I guess it's not zero, but not well defined. But is there a reasonable way to get an answer here, like with this technique, with this SIQ trade-off type of thing? Can you tackle this?
I'm not sure if I understand your question correctly. So can you write so some using some pencil or something? No.
I am sorry, I'm using Linux, so I cannot write.
Okay.
But such is life. I was just asking. I was wondering if you can extend this technique to also look at the final state of this auxiliary system.
Okay. The answer is yes, indeed. Yes. So we can extend. More precisely, maybe yes.
Okay.
So there is prototype version of this result, and in the result, indeed, we consider the Fisher information in final state of the external system.
Okay.
So maybe we can use similar relation, and we can obtain the bound for Fisher information in here. Maybe, but this is just maybe. Yeah.
Okay.
Okay, very cool. Thanks, Hiroyasu, and I will stop the recording here.
Yeah.